We begin lecture 5. We will as always do a quick summary of the key points from lecture 4. This class we will look at a mathematical framework for sampling and reconstruction. Again, this is a useful tool for us as we move between the continuous time and the discrete time domains. We will look at a specific example of discrete time processing of continuous time signals. As you probably have studied in DSP, there is also continuous time processing of discrete time signals, because you are able to go back and forth between the two domains, and we will look at that. And as we mentioned, having given this framework for sampling and reconstruction, we are now moving into the topic on discrete time signals. So just to sort of change the pace a little bit, I thought that let's take a look at the examples that which I mentioned in the last class, and we'll just do a quick run through of the of these examples, and just as an illustrative exercise. Okay, so I think I'll make a small change. There is one more. I'll add one more sample to the. Okay, it's a 6 sample sequence. So if you were to think of this as a sketch of the sequence, at time 0 you have a sample equal to 1, time 1, 2, this is 1, 2, 3, 4, 5, 6. Okay, so 1, 2, 3, 4, 5 is the time index. Am I right? No. We are told that the sample number 3 is the is 0 index. So the 0 index actually happens here. So this is sample number 3, 0, 1, 2, 3, minus 1, minus 2. Please make sure that the arrow is a key indicator. So the height of these are 1, 2, 3, 4, 5, 6. Okay, that's the. So let me just quickly write down the answers just for discussion and sort of refresh people's memory. So y1 of n is equal to x of n minus 3. So if I were to write this down, I won't write down the expression, just write down the sequence 1, 2, 3, 4, 5, 6. The origin has moved three places to the left. So the sequence, if you were to go look at it, it had 0 valued samples here. Now it moved from 0 to minus 3. Minus 3 was where the origin now lies. So that is the sequence for sequence number 1. So y2 of n was x of minus n, basically a time reversal. So that would mean that the sequence will now go backwards 6, 5, 4, 3, 2, 1. The origin remains as before, so basically remains at 3. Then the interesting cases come at 3, 4 and 5, x of minus n plus 1. Again, there are several ways to do it. There's the shift operation, there's a time reversal operation. As we have as we always emphasize in the DSP course, always easier to do the shift first, because otherwise the shift becomes a little bit tricky for us to handle. So the steps that I would suggest is write an intermediate sequence y3 dash of n, which is x of n plus 1. So you've taken care of the shift. So this will be a sequence. N plus 1 means you are advancing the operation by 1. So 0, 1, 2, 3, 4, 5, 6, okay, and zeros be outside of that range. Basically the advance operation says that the entire sequence moves to the left. So my the origin now becomes 4. From originally it was at 3, the whole sequence has moved by 1 unit to the left, and then the next step you get is y3 of n is y3 dash of minus n. So that you can verify is actually x of minus n plus 1. But it's much easier to flip y3 of y3 dash of n. So basically the sequence would be 6, 5, 4, 3, 2, 1 and with 4 being the origin. So, basically you time reverse the sequence with that. Okay. And y4 of n is x of minus n minus 2. Again, I won't, I'll assume that this is a just a direct extension of the previous case. You shift 2, that means you shift the sequence to the right by 2, you are delaying by 2 units of time, and then doing the time reversal should be straightforward. Okay. y5 of n, this was x of 3n minus 1. Okay. And the way to do it would be define an intermediate sequence which gives you the shift x of n minus 1, and then you can get y5 of n with a time scaling of y5 prime of n, y5 prime of 3n, which will come out to be x of 3n minus 1. It turns out that if you do one operation per step, it is much easier for us to actually keep track of the. So, x of n minus 1, I am assuming you know how to generate. Then the key step is, the next step is the scaling of time. So, rather than work with a sequence, I thought it is helpful to form a small table. So, if you say n is equal to 0, 1, 2, the argument of the function that we are trying to compute with the time scaling and the shift is 3n minus 1. So, this would be minus 1, 2 and 5, and x of 3n minus 1, x of minus 1 is 2, x of 2 is 5, and anything outside that range will go to 0, and this becomes y of n. Okay, so, this is the that becomes y of n. Now, I am assuming that these are fairly rudimentary examples which you are quite comfortable with. What I would like to do is just mention, and we will come back to look at several examples both in the class and in the tutorials. So, this is the general case. If I am given a sequence x of n and I am required to obtain y of n equal to minus m by n times n minus n naught. Okay. Notice that this particular transformation has got a shift, it has a time scaling. It has got a time scaling both in terms of compression and expansion. So, there are actually time scaling of 2 kinds, okay, 2 types, both types of time scaling are present, and the third one is the time reversal. From the point of view of multi-rate signal processing, this is of a lot of interest to us, but it usually happens in the context of shifting and occasionally time reversal as well. So, this is a form of transformation that we are very much interested in the study of multi-rate signal processing. So, here is the general guideline. The sequence in which it is easiest to do is to do the shift first, then the scaling, and then finally the last stage would be time reversal. It is easiest if you do that, minimizes any possibility of careless mistakes. Of course, these two can be interchanged without too much difficulty, because they are processes that do not really you can do it in either sequence, but the sequence of shifting, scaling and time reversal is a very robust way. You will not make mistakes there. So, the steps that we would like we would do here. So, first step would be define y prime of n x of n minus n naught. Then the second step is to do the sampling rate expansion. y2 dash of n is y dash of n by m. So, as we will define this process, this is the process of expanding the sampling rate, and this will also end up inserting a lot of zeros. You do not lose information in this step. So, always better to do this step first. I think we divided by n, I am sorry, this should be n. Okay, so sampling rate expansion comes next, and of course you can substitute and verify that this will give you a signal which is x of n by n minus n naught. By the way, m, n naught are all integers. That is the assumption in terms of the basic transformations that we are looking at. So, y triple prime of n is y double prime of mn. This is the sampling rate reduction. You retain 1 out of m samples. This corresponds to y dash of mn by n, that corresponds to x of mn by n minus n naught. Okay. And the last step is the time reversal. Y of n is y triple prime of minus n. I have done the scaling. So, the last step will be and this will give me y double prime of minus mn, that will give me y prime of minus mn by n, and that will give me x of minus mn by n minus n naught. Okay. And of course, there are several simple examples that we can try out, but this is the most general case and good for us to keep that picture in mind. Okay, so discrete time signals, do take a look at Oppenheim and Schaefer chapter 2, basic properties, basic operations, and also built into it the understanding of the DTFT and its properties. So, again that would be a quick review. Assignment written assignments have been uploaded. Do take a look at Moodle. If there is a difficulty in accessing Moodle, please do indicate to the TAs or indicate it on the attendance sheet. Okay, now we would like to sort of revisit our sampling and reconstruction one more time, again to build on the mathematical framework, and let me just take that as the next step that we would like to do. Okay, so the sampling process is given in the expression in the lower half of the screen. Basically, you are doing periodic sampling, and there is an understanding that we must ensure that there is an anti-aliasing filter to be in order to minimize the risk of aliasing, to avoid aliasing completely. And of course, the ideal reconstruction filter, which we have been talking about, is a brick wall filter from minus omega s by 2 to omega s by 2. We can also relate it to the sampling period minus pi by ts to pi by ts, and the actual expression is a sinc function which we derived in the last class. Okay, now I would like you to follow along on one of the aspects of the mathematical elements. So, let me first write down the continuous time portion and then relate it to the discrete time. X s of t, the sampled signal, this is x of t multiplied by the impulse train, n equal to minus infinity to infinity, the Dirac delta t minus nts, and this has a Fourier transform which we have derived, which is x s of j omega, which is given by summation n equal to minus infinity to infinity. Basically, if I were to write down the do the Fourier transform of this, you will find that when I apply the integral to the Dirac delta, what the expression that I will get is summation n equal to minus infinity to infinity xc of nts, right, that will be the value of the function, and e power minus j omega nts. The integral will leave you behind with just the summation. Okay. So, basically I am taking the Fourier transform of x s of t, okay, which is the expression on the right hand side. Okay. We have looked at it from a different angle, where we said we multiplied the Fourier transform, we convolved the Fourier transforms of x of t and the Dirac delta train. This is another perspective of it. Okay. So, basically this comes directly from the following observation, that this summation is nothing but n equal to minus infinity to infinity xc of nts delta of t minus nts, basically the sampling property of the Dirac delta. And then if I want to take the Fourier transform, I have to take integral of xs of t, and then the integral basically because of the property of the delta function gives you the expression on the right hand side. Okay, so that is one piece of information. Now moving over to the discrete time domain, x of n is xc of nts, okay, and of course n is the periodic sampling where n equal to 0 plus minus 1 plus minus 2 and so on. For the discrete time sequence, we define the discrete time Fourier transform xe of j omega as the following: summation n equal to minus infinity to infinity x of n e power minus j omega n. This can also be written as summation n equal to minus infinity to infinity xc of nts e power minus j omega n. I have two equations which are very interesting and important. One is equation number 1, second is equation number 2. Both are Fourier transform representations. They are Fourier transform representations, one in the continuous time domain, another one in the discrete time domain, of the same signal, because the sample sequence xc of nts when represented in the continuous time domain gives me Fourier transform given by equation 1. The discrete time sequence represented by the discrete time Fourier transform gives me equation number 2. So they are basically one and the same representation. So the next step is a very important link between the continuous time and the discrete time, which basically says, comparing 1 and 2, we write down the following: xs of j omega has to be the same as xe of j omega, xe of j omega evaluated at omega equal to omega ts. That is the relationship between the continuous time frequency and the discrete time frequency. So this is in the discrete time domain. If you have xe of j omega, you are equally it's equally valid to write it as xe of j omega ts. Right, because instead of using the relationship omega is equal to omega times ts, uppercase omega times ts. So using that expression. So basically comparing 1 and 3, we write down the last of the equations. Again, you may wonder why are we spending amount of time on this. It actually is a very important element, this link between the Fourier representation of the continuous time sequence and continuous time signal and the discrete time sequence. So xe of j omega ts can be written as, comparing 1 and 3, as 1 over ts summation k equal to minus infinity to infinity, because x of j omega we already have derived to be equal to this expression. So this would be xc of j times omega minus k omega s. This is an independent, basically another form of xs of j omega. So this is equal to xs of j omega. This is again derived in the earlier lecture. So this also tells us that we can also write the same equation, equation number 4, in terms of the discrete time omega, which says xe of j omega. How do I visualize it? This is the representation, periodic repetitions of the continuous time frequency with the appropriate scaling of the frequency axis. So it is 1 over ts summation k equal to minus infinity to infinity xc of j omega by ts minus k times 2 pi by ts. Okay. So basically what we are saying is, the signal, if we view it in the continuous time, gives you a certain insight and representation. You view it in the discrete time, it gives you certain insights and representation. And when we are doing this process of sampling and reconstruction, we are going back and forth, and very useful and helpful for us to have a clear picture of what is happening. Okay. So, we do have copies of the spectrum which are given in the last equation, and the condition that you do not have overlap of the spectra, the conditions for no overlap. So, basically if you want to impose the condition that non-overlapping of the copies of spectrum, this, if you want to impose this condition, this would basically boil down to, you can look at it in the in terms of the pictorial representation, or you can again go back to how this this expression actually came about. The first thing would be is C of j omega must be band limited, right. If it was not band limited, anytime you have multiple copies, they are going to overlap, and we also must ensure omega s is greater than or equal to 2 times omega naught, which is the band limit. Okay. And again this omega s is nothing but this 2 pi over Ts. So, once you have ensured that your shift is larger than 2 times the bandwidth of the signal, then that again goes back to the Nyquist criterion, and then so we can look at the Nyquist criterion in the continuous time domain, which is very straightforward for us. But when we look at it in the discrete time also, there is a insight that we can talk about in terms of make sure that you have sampled it at a sufficiently high rate, and that is very important for us to have this picture as well. Now, this relationships that we have derived on this page will become more familiar and useful once we start talking about the discrete time processing of continuous time signals, which is what I would like to do as part of today's discussion. Okay, but before that, always interesting for us to look at some interesting examples, and so what I would like to do is share with you an insight of one of the very powerful applications of DSP as a baseline, and in particular multi-rate signal processing, which you probably are using in everyday life, but may not have associated it with that particular application. Okay. So, the application itself is in the context of music. So, it is in the music and very specifically in playback, okay, which most of you I see today, even as I was coming to the lecture, so a lot of people have music plugged into their ears while they are coming to class. So, you probably used it hardly a few minutes back. Now, one of the things that I am sure you enjoy using on your music players is the graphic equalizer. You set it to the way you like to hear the music, and one of the options that you will have in high-end players is to give you certain sound effects. It can give you the sound effect of a jazz setting, or you can have a rock setting, or you can have a concert hall setting. So, I would like to just sort of take you to a concert hall. Okay, let us say that you wanted to look at the concert hall setting. Okay. I do not know how many of you know that in Chennai we have a absolutely wonderful concert hall called Music Academy. If you do get to hear it, you can sit anywhere in the auditorium. You do not need mics, you can hear it without amplification, and that is the beauty of it. But it is a auditorium that has this sort of a effect. It is a sort of a circular auditorium, and the best seats are somewhere in the front. It's somewhere in the sort of the not exact geometric center, but it's somewhere close to the front. Okay. Now, if you do analysis of this type of a concert hall and see why is it that the best seats are somewhere. So, basically if you were to think of it, I'll just draw it. Okay, something of that type. Okay. Now, why is it that the best seats are there? It sounds basically the acoustics is designed such that if you are sitting here, you get some sort of an optimal combination of the different echoes of the signal, copies of the signal. So, basically what you get is, one is the clarity of the signal, second one is the feeling of depth, that you are in an auditorium, because you do get a certain, and people have done analysis of this what produces this type of effect. So, basically from a signal processing viewpoint, there is a direct path. Basically you do get a signal that is coming directly from the source of the music, or but there is also multiple copies. So, if you were to characterize the received signal, so there is a direct path which arrives, okay, this is in microseconds. So, there is a direct path, and there are several other copies of the signal, and what is, and basically if you look at the acoustics, what is the what makes a concert hall very good, acoustically excellent, is that there are certain copies that come because of what they call as early reflections, okay, some which is coming from nearby, from where the sound source. So, these echoes are referred to. So, this is the direct path, this is the direct path, then there are early echoes, and then there are the reverberation. So, basically these are slightly longer term echoes, and eventually this dies down. Okay, these are called the reverberation components. Now, those auditoriums where you get absolutely the perfectly designed and or created environment where you have optimal combination of these echoes and reverberation, and particularly in locations where you sit, and therefore you enjoy the best of music. So, but all you have is a CD player and a set of headphones. So, now how do we create this effect? So, basically instead of playing only the direct path, see, if you played only this, that will be just a simple CD player microphone. But if you have a equalizer setting which says, okay, concert hall, then you basically must not play back only the direct one, but you must play back the composite signal that we have to develop. Okay, so the multi-rate signal processing comes into play when we say that, okay, I take the sample signal x of n, there is a direct path, and then there is a bunch of delays, different delays from which we will get the early echoes. In a hall you do not have to create this comes automatically, but when you want to do it on your CD player, you have to create that. And then you have a second set of delays. These are different delay components, which you then these correspond to the reverb signals, several of them. You have these reverb combinations, and all of these, if you combine together with suitable phase, and lots of the things are there when you handle acoustics, you must combine them in a suitable fashion. So, I will just put a big plus sign here. This produces for you a y of n, which will be similar to what you would have gotten had you sampled the signal that is being received at this red dot. All you have is a direct path, but you have artificially created these multiple things. These are the early reflections, and these are the reverb components. Okay, and this is what will then get passed to a D to A converter and then played back through your stereo headphones. Of course, you can create some differential signal. You can create a left speaker signal, right speaker signals differently from using the same combination. So, but ultimately the basic principle is this. Okay. So, you can actually create any sort of acoustic effect concert hall, rock band place where rock. So basically you will set the settings, you will set the frequencies, maybe you will boost the bass. So but in effect what we are producing is a very interesting combination of these components. Okay, now where is the multirate part? Where is the multirate part? I didn't see any multirate. It's just samples which you delayed and multiplied, and so that's what will actually happen. If you end up in a situation, so let's take for example that you had CDs, you were playing back CD music. So CD music is at 44.1 kilohertz sampling rate. Sampling period is approximately 22.7 microseconds. The samples of your music are coming at a sample spacing of 22.7 microseconds. Okay, so some samples are coming, this spacing is your TS, which is 22.7 microseconds. Now anything that I do in the form of a delay, if I want to implement a delay in digital domain, it will be z power minus n naught, where n naught is an integer. N naught is an integer. Okay, so I can only get multiples of basically the smallest delay that I can get is z power minus 1, and if I delay it by one sample period, this would correspond to 22.7 microseconds. Okay, 22.7 microseconds. But in the construction of the of this concert hall effect, you cannot restrict yourself to say no, give me only delays and multiples of 22.7. Sometimes there are the signals that are coming at different delays. So as an example, supposing I want to combine direct path, okay, so that would be x of n, let us call that as a naught, some scale factor, plus a1 times x of n minus delta, where delta is 10 microseconds. Okay, suppose I just want to combine this, and of course in a concert hall effect there will be several combinations, and so I am just taking the case of one. So now this is a case where you can say, well, too bad, either so if let us say you want to get 10 microseconds, this is total is 22.7 microseconds. So we say, well, you can either choose to either not delay it or delay it by 1 unit, which will move it to 22.7 microseconds. We say, okay, both of those are not acceptable. So then we say that, okay, let's see if we can do something simple, and supposing, so we say that, okay, I do 2 times oversampling. Okay, so the problem statement, I want delta equal to 10 microseconds. My TS is 22.7 microseconds. So basically this is approximately equal to 0.44 TS, 0.44 TS. So if I now do 2x oversampling, that means I create, this is the original signal, this is a sample spacing of TS. I know how to increase the sampling rate. So I introduce a new sampling point here at TS by 2. 2x oversampling means that I can reduce it. So that means I will get samples at 0.5 TS, TS, and so on. Every 0.5 TS I will get. So basically I have increased the sampling rate by a factor of 2. I want to get 0.44 TS delay. I can't get 0.44, the best that I can do is this can be approximated. So delta equal to 10 microseconds can be approximated as 1/2 or 0.5 TS. 0.5 TS, instead of 0.44 TS I got 0.5 TS. Okay, you say, okay, that's okay, but not quite all right, because I am doing very high end, I want to reproduce, so I want to reproduce the concert hall very precisely. So then we say, okay, I will go to a 10x oversampling. 10x oversampling says that yes, now I can introduce delays in my signal, which is of the form of 0, 0.1 TS, 0.2 TS, all the way to 0.9 TS, and then Ts. So, basically in between two sampling points we have gotten 9 other sampling points. So, that is the 10x oversampling, okay, and somewhere here is 0.4 Ts, and of course 0.44 means that the closest one will be 0.4 Ts. I can introduce a signal of that form, okay, and of course if you are very picky, you can even say okay, go to 100x oversampling, not a problem. Multi-rate signal processing can do the oversampling fairly easily, and which means that you can get delta is equal to 0.44 Ts if you want it very precisely. Okay, so again it is an interesting way to look at the problem. It says that I want to recreate the concert hall effect, which means that I must recreate with several signals of several delays which I need to combine. I cannot, that depends on the acoustical properties and not necessarily on my sampling period. And if I want to achieve something that is very close to what I want to implement, in the ideal case, then multi-rate signal processing is a very useful tool, which I think we can exploit, we can use and exploit and take several lots of very good advantages from that. Any questions on what we have said? Why multi-rate even comes into play?
So the D2A block is running at 44.1 kHz.
Well, you can run it if you have done the oversampling, unless you have done the downsampling before doing it, you would have to run it at a higher rate.
We cannot do the downsampling because we want the concert hall effect.
Okay, wait, that's a very good point. So basically what we are saying is you create, so it is like this. Easiest if I show it to you in a continuous time signal. So I have something which is like a music signal. Now I must, what we are trying to do is, so the important thing is that you have been able to create the signal with the appropriate delay. The bandwidth has not expanded. So though I have gone to a higher oversampling factor, the bandwidth of the signal, I have only introduced a delay. So basically it is an acoustic effect, I have not changed the bandwidth of the signal. So I am perfectly able to think of this as a signal for which I can go back to the original sampling rate. So I may have gone 100x oversampling I might have done, but I can still go back to the original sampling rate without losing the quality of the signal, and I will not lose the effect of the acoustic effect, because this has already been produced. Now think of this as the sum of the green signal and the red signal. Take the sum of it and then sample it, which means now you have a signal which has the acoustic effect built in and is at the right sampling rate. Of course, you can need not go down to the lower sampling rate, because the oversampling actually helps your D to A conversion. So you can actually say that anyway I want to do oversampling to do a good D to A conversion, but in principle this is what we are trying to do. So you have actually introduced the effect using the multi-rate part. You can go back to the original sampling rate if you want to, or you can retain it and then go to the D to A process at the higher sampling rate. But a very good question, yeah, because we will not lose the effect of it, because see the effect of the acoustic processing that we have done basically says that I have created the effect of another echo, and the combination of these two has already been incorporated. So even if I go down to the lower sampling rate, I will not lose the effect of the signal. Okay, any other question?